Okay, so yeah, so we will go from the movies to the particles. So the first step is this movie alignment. And for the movie alignment, I would like to show how a frame looks like. So a frame looks like something like that. So just some spots. Actually, the typical dose per frame is about 1 electron per angstrom squared. So that means that the most typical values that you observe in your pixels are 0 and 1. And so this follows a Poisson distribution. So the most typical values are 0 and 1. And then you have very few 2s, 3s, and very rarely you have something bigger than 10. So these frames have extremely low signal to noise ratio. And then you have to find alignment between all possible pairs of frames. Depends on the algorithm how they work, but this is a reasonable way. And the thing is that all these shifts will have a lot of noise. So the algorithm must have some robust way of identifying which shifts are incorrect. And for that, one of the regularizations that most algorithms have is to limit the maximum shift that they can find. So if you can expect only local shifts, then you can have a particular trajectory. And here you can see the change in the trajectory estimated if you move the maximum shift from 40 to 80. So it can have a significant impact. So you see, this is with 80 maximum shift, 40 maximum shift, and this is with 80. And this maximum shift is between one frame and the next. So this parameter that we normally don't care about it can be critical. And also, it is not yet ready in Cypium, but with this later work, what I'm presenting here is the results of Motion Core 2, Rely on Motion Core, and Flex Align. That is the new algorithm of XMIP to do this frame alignment. It is using GPUs for that, and it is not yet in Cypium, but we plan now that if you do two movie alignments, you can compare the trajectories and check whether one of the algorithms have made a big mistake. You can only compare these algorithms at the level of global shift. That is the one that I'm presenting here in this plot. But it is already enough to check if there is a catastrophe like this one. So one of the movies is completely unaligned if you use the incorrect parameters. But you never know which are the correct parameters. So in practice, it could mean that you try with the default parameters, and then you check the trajectories. And if most of them agree, that's fine. But if you start to see many mismatches between two different algorithms, then probably one of the two is wrong. And this is another idea that I would like to introduce. That is, all these algorithms, they have in one way or another some way to estimate the local deformation. So in the plot, we have the global deformations. That is a single shift per frame. But then we can, at every possible tile of those micrographs, we can compute local shifts. And depending on the number of parameters that you use and number of tiles, that is some way of specifying this for each one of the algorithms is different. But if you use too few, then you are not going too far away from the global shift alignment. If you use too many, probably you have distortions, especially at the border. The borders are very ill-defined because they are less constrained in most optimization problems. And then just using somewhere in the middle is the right thing. With real data, it's very difficult to realize which one is the correct one. We have found some reasonable range for most of the algorithms we use, and I'll show you later some results with phantoms. So here you have the same idea. So the same idea, but now with a different parameter. And this other parameter is a low-pass filter that you may apply when aligning the frames. So the thing is that these frames have so little information that you need the shifts. You cannot compute the shifts between two consecutive frames because there is almost no overlaps between the pixels. Most of them are zero. So you have to blur them a bit. How much is we have found that something like 30 angstroms is a low pass filter at 30 angstroms normally is good enough for this kind of filters. But then we found a movie for which, or a data set for which these 30 angstroms was giving completely incorrect results. And well, completely incorrect. You see, this is the right, this is the correct trajectory, and this is the incorrect trajectory. And if you look at the axis goes from 0 to 1.4 pixels in one of the directions. But and this one is only 1 pixel off. So in the whole movie. So this is still a very accurate result. But we were not happy with that, and we discovered that it was this low pass filter of 30 angstrom. If you put it at 10 angstroms, then it was correct. And when we went to the frames, this is what we saw. So somehow in this data set, the frames had been pre-processed, and then the pixels didn't look anymore like this Poisson distribution. So this is again a warning. You have the simple fact that you use a motion correction alignment program, whichever it is, doesn't mean that you are on the safe side. Okay, so I had my movie, I have aligned all the frames, so now I have the perfect information coming from this movie, and this is not the case. All programs have parameters. Of course, we analyze in more detail the parameters coming from XMIP because that is what we developed. But I'm sure that for all other programs it is the same. I'll show you now another example with Motion Core 2 and Motion Core 2. So this is the analysis, and this is again going into the same direction. Never believe blindly anything that any program says, even ours. So believing blindly program outputs is really, really bad. So this is the micrographs after aligning some movie data set. And here what you see is that on just visually you see different contrast, which is some of them seem to have a more higher contrast than the other. And when you go to the power spectra, what you see is that for some of them, you see, for instance, this is the case of Motion Core 2. In this particular case, it doesn't mean that Motion Core 2 always has this problem, but you have to be careful of this. For instance, it was having aliasing. So you see that at high frequency, the energy is highly boosted. And for the others, for instance, these two, there are two that are almost one on top of the other. These are the two from FlexAlign, and this is a Rely on Motion Core. And they all start with the same energy, but then at some point, the Rely on Motion Core is attenuating more, even if it has kind of kink here, and it is attenuating more the high frequencies. So we think that this isn't related to the final interpolation, might be, but we don't have clearly what is the reason for that. But again, do not believe blindly that any program output. It might have attenuation at high frequencies because some interpolation, some particular problem like this one of aliasing. You can also see here it is a little bit of small, but if you look at how the CTF is oscillating, you see that some of them go a little bit farther than the other. So there is a bad custom all of us do, that is just using one program for the movie alignment, and we are happy with its results. We don't check anymore what it gave. But actually, there is a lot of details there. And this is another example. So this is now with a phantom. And with this phantom, we created some kind of elastic deformation so that in the corner, there was a bending of the grid. And if you don't do anything, you have a blurred grid. Then we simulated data following this Poisson. So in the frame, you almost don't see anything. And if you align with flex align and choosing more or less the default parameters, you are able to recover the grid. If you use motion core, you also recover the corner of the grid. And the corner is where it was deforming the most. So if you go to the middle of the micrograph, the middle look nice. But if, for instance, if you think that the sample is going in a doming, supposedly a doming or any other kind of effect, the corners may be important. Then motion core in this particular example didn't give very good result. And here is an example of how changing the parameters of motion core 2 changes the output. So here you have with the default tiling that is 5x5, here with 7x7 and 9x9. So the result with more tiling is more accurate. And we know this for phantoms. For real data, it is impossible to know what is happening. Here is another example of how to look carefully at the output of every step. So again, this is the movie alignment step. And when you look at the histograms of the output micrographs, you see that for this particular case, the histogram of motion core 2 seemed to be clipped. So the low values somehow were saturated. And this was not the case of flex align or rely on motion core. And also the spread of the rely on motion core and the spread of flex align, they are different. And this in principle shouldn't be much of a problem because later all particles, the extracted particles, will be renormalized. So they all will have zero mean and standard deviation 1 in the background. So yeah, here you have a bigger picture of these power spectra. And here you can see that the oscillations are different. They go up to different frequencies. And so I will show you where this is in Scipion. So in Scipion, you import your movies, and here, if you are close to the microscope, in the sense that you are acquiring at the same time your movies, this import movies is working in streaming. So you say from which directory you want to import your movies, you specify the pattern of the movies, then you give the acquisition parameters, and then by default, this one is working in streaming. So this should be coming. And this was not the case because we didn't acquire the data, but you can process the data in streaming, and then all the steps below, as soon as a new movie appears, it starts to be processed. And even you can, for instance, remove some patterns that you know that you don't want to import because they don't. They are, for instance, atlas pictures, or for some reason you don't. There has been, for instance, a previous import that crashed, or you stopped, or whatever, and then you want to import only the new movies. So you can take some of the particles, some of the movies, and say, I don't want to import these ones. And there are many different ways of saying what you don't want to import. And this one is related to whether all the frames are in a single file, and that is normally now the case, but some years ago very often frames were recorded as separate files. Okay, so you import your movies, and then you go to movie alignment, and here you would have all the possibilities. And you have system and blur. I don't have all the plugins installed, so I just have a few. And for instance, Motion Core 2 is not appearing here because we run it on some other machine. And so you have Rely on Motion Correction, Motion Core from, this is the one from Motion Core 2. And then the one from FlexAlign from XMIP is here, but you have it only in the development branch, not in the release one. Actually, there will be a Sapien 3 release very soon, in about 1 month or a couple of months, and all these algorithms will be released. But if you want to use them, you can have access to them by installing the development branch. But actually, it is not called Devel, it is called Python 3 migration. Okay, so you do your motion alignment. In this example, I used only one algorithm because we don't have yet the trajectory comparison. So I used just one. The one that you use also makes a difference in the sense that if at the end of your process you want to do polishing, most polishing programs, they assume that you have done the motion correction with one particular program. So for instance, if you use Rely on Motion polishing, it requires a Rely on Motion correction. If you use XMIP polishing, you require an XMIP motion correction. And so the next step is to compute let's see if there are some specific parameters here that need some comment. In general, in all motion correction programs, there is the option to not align all possible frames. So for instance, if you know that your last frames have been more or have a dose damage, so you may say here only compute the micrograph from 1 to 10 or from 1 to 20, those frames that you trust, and then the remaining from 20 to the end, they will not be summed. And you can do dose weighting or not. Dose weighting, in principle, dose weighting is using a kind of universal formula that in principle does not need to apply to all possible samples, all possible microscopes, and all possible acquisitions in the world forever. So sometimes they help, this dose weighting. Sometimes it doesn't do any harm, and sometimes it hurts. So it produces worse results. And unfortunately, there is no way of knowing which is your case other than trying and see if you get better results by changing this dose weight. The polishing is in principle a way to do also this dose weighting in a more clever way. So so in principle, normally we seldom touch these parameters. Rely on Motion Core is in CPU, but you can use multiple threads to compute it. And it takes about 1 minute per micrograph, depending on the size and so on, but it takes about 1 minute. Okay, so let's go back to the next step. So the next step is the CTF determination. And so for the CTF determination, we have here an example of CTFs fitted by XMIP, and they look good. So as you know, this is the experimental power spectrum, this is the simulated power spectrum, and you have to check that the zeros of one are also the zeros of the other, and in principle they coincide. Visually, you don't see any difference, but then you know this result. So if you want to, this is coming from a relatively old paper, but I think it had a very nice ideas. So if you want to reach very high resolution, you need to have an error in the defocus estimation that is at most around 100. So this is a really accurate defocus estimation, and this is actually what we discovered in this project that I'm showing you. So you know that if you compare different algorithms for CTF estimation, this is unfortunate that this label came on top of the logo. But for instance, in this paper, we compared different algorithms in the CTF challenge, and the range, the error range between different programs was somewhere between 200, 300 angstroms. So that in principle may look to be accurate enough. Actually, if you look at the power spectra, you don't notice any difference between 200 up or 200 down. But we discovered in this project that you really need the CTF to be really accurate if you want to extract the most from the micrographs. So we were having very limited resolution, and we got only to improve it only when we asked the two CTFs. So we estimated the CTF with two different programs, and we asked the two CTF to be consistent with each other up to 2 angstroms. 2 angstroms was 2.1 was Nyquist. So we required both estimations to be consistent. And the thing is that all these estimates, they are estimates of parameters, and in any parameter estimation there is noise. And the noise, this paper gave us more or less the range of the noise that we are having. So it is some oscillations around 200, 300 angstroms. So only when you have very accurate defocus estimation, you can reach a high resolution. And this is what we had here. So let's go back to the project. So I estimated the CTF with GCTF and CTF find fault, that are very well accepted programs in the field. And these only estimate the defocus, but they are pretty accurate. And then I computed the consensus between the two. So the consensus between the two is something like this. So you use one of them as reference, no matter which one, the one that you like the most. And then you can use different parameters to filter your output. So you can use, for instance, the defocus has to be between 0.4 microns and 4 microns, or the astigmatism cannot be more than this, or the resolution cannot be less than 17 angstroms. So this 17 angstroms is kind of meant to avoid catastrophes, absolutely wrong estimates of the defocus. Yeah, but in this example, I didn't use any of these options. None of these two CTF estimates are coming from XMIP, so we don't use the XMIP criteria. We will see the XMIP criteria later. And I was using the consensus between the two. And so you take now the second estimation of the CTF, and you ask both estimations to have to be consistent up to 2.1 angstroms. So they're consistent, but so consistency means here that if you draw the CTF profile, the two CTF profiles do not differ more than 90 degrees, I think. But they can differ. And they differ because the defocus estimates are slightly different. And this is slightly different, but now if you see that two of them are slightly different only, a better way, I'm thinking in terms of parameter estimation. So you have two estimates of that parameter. So if you average those parameters, you would have a better estimate of the underlying parameter. And this is what this consensus is doing. And then this is a flag just to take all the possible labels that you get from the different CTFs. And then what we see here is that only 2/3 of the micrographs can be estimated so accurately. Doesn't mean that the other third is not good. It doesn't are not good micrographs. It means that I cannot trust what is the defocus parameter. I don't know. One of the programs is saying something, the other program is saying something else. If you look at the power spectra, they more or less look the same. So I cannot decide which one of the two is correct. And then I have to leave these micrographs apart because I cannot determine so accurately the defocus. And then you can have the CTF estimation. And here the CTF estimation of XMIP is there is a way, and this is only in development, of because I trust so much this parameter that I have estimated here of the defocus. Now I don't want to touch that defocus. And before, in the released version, we were taking the previous parameters and trying to refine it a bit. But now we think that refinement might be introducing a little bit of more noise. And then we can see now, I thought I had it, the CTF consensus with XMIP, but I don't. But it's not difficult to see. So we can take this tab, and then we say that we want to use the XMIP criteria. For the XMIP criteria, the primary CTF has to be XMIP. And then you have many different possibilities. So where is the minimum, the first zero? What is the astigmatism at the first zero? So you can limit astigmatism there too. You can also, for instance, look at the correlation between the first and the third zero. Sometimes you see that the tone rings, they fade too quickly, and then this is not good. This CTF margin is also more or less the same, that it is looking how visible the rings are with respect to the noise that we see on the rings. And then deciseness is if a micrograph has eyes, and we have some way of measuring what is the power spectra, the energy at 3 angstroms, at 4 angstroms, and then the ratio should be smaller than 1. If you have something larger than 1, is because you have eyes. And this non-astigmatic validity, that I will come back to this now in a moment. This non-astigmatic validity has to do with the fact that the two defoci that you are estimating in two perpendicular directions, they're different. And so if they are the same, the micrograph is perfectly astigmatic. If they are perfectly non-astigmatic, if they're slightly different, that means that in one direction the oscillation goes slightly different than the oscillations in the other direction. And unless you are very careful in the 3D reconstruction, and normally the 3D reconstruction is not very careful about that, the polishing is, but unless you are very careful, these slight differences in the oscillations might limit your resolution. I'll show you now an example of that. So here you have, so let's go back to the presentation. Just a reminder, if you want to comment anything in between, just unmute yourself and we comment on it. So here is an example taken from the EMDB. And very often, these are slices, these are projections of the volumes. And very often, we see some kind of dark halo around Maybe in the slices, sometimes in the slices it is very obvious. When you project the volume, it is even more obvious because all these dark halo contributes, they are added together. And then, this is not a criticism to this particular entry. So there are many entries like this, and we all produce this kind of data with dark halos around. And it is well known that these dark halos around, they are caused by an incorrect CTF correction. And here you have an example with it is experimental data, but that we have artificially distorted. So here you have in a slice of the 3D reconstruction made with the best CTF defocus that we can estimate. But then I systematically biased all the defocus by 20%. That is more or less half a micron in this data set. And then there is a dark halo around. I don't know if you can see well on the screen, but there is a dark halo. And we all live with this dark halo. So it is very easy when you go to Chimera, you put your threshold. Actually, dark means negative value. So as our thresholds are positive, they don't disturb. But the problem is that if you compute the difference between this reconstruction with incorrect defocus, with this one, with the best defocus we could find, there are not only the dark halo, that is these black values or dark values around, but there are also differences in the structure. So inside the structure, there is a lot of small details that are different between the reconstruction you can do with your best defocus and the reconstruction you can do with some defocus. And the same happens with the pixel size. So the pixel size, if you look at the formula of the CTF, the pixel size goes indirectly through the frequency. So if you have oscillations in the pixel size, and we are all doing that in the polishing when we are trying to optimize the scale of each one of the particles. So we have to be very careful about this scaling, so that it doesn't move much, because otherwise, if we estimate incorrectly those parameters, we will be introducing this kind of effects in the 3D reconstruction. And here is this non-astigmatic validity. So if you look at the resolution reported by the CTF programs, for this data set, it tells you that you have very high resolution up to Nyquist. Probably this is an overestimation, and the defocus, depending on the program, but sometimes, so it sometimes overestimates quite a bit the resolution. But still, you might think that simply by having energy at high frequency, you have a high resolution. This may not be the case, and this was the case of this example, because the energy that you have in both directions, in the direction U and V of the 2D focus, they might be different. So as the 3D reconstruction is assuming perfectly non-astigmatic images, if your 2D focus are different, then you are violating this non-astigmatic assumption. And this is a plot that is computed with the XMIP CTF of at which frequency, at which resolution we are violating this assumption, such that the two waves of the CTF, they are completely out of phase. So they are completely with a phase shift of 180 degrees. So, and you see that for most of these micrographs in this data set, this assumption completely breaks at between 3 and 5 angstroms. So there are only, let's say, 1/3 of the micrographs that do not violate this assumption. And actually, this was the case. So this this reconstruction that we will not go today to the 3D reconstruction because we are just going to the particles, but this reconstruction is limited. The resolution is limited about 3-4 angstroms. So, and I have already observed this in some other data sets, that the non-astigmatic validity is a very good predictor of what will be your maximum resolution. And so the fact that you have energy at high frequency doesn't mean that you will be able to have a 3D reconstruction at that high resolution, because all programs will assume that things are non-astigmatic, and the astigmatism may play a role. The thing is a bit like in this plot here. If you want to have very, very, very high resolution, you have to be perfect in absolutely all steps. So you have to be to correct your motion perfectly. You need to estimate your defocus perfectly. You don't need to have astigmatism. Polishing is a kind of a cure to that, but it doesn't mean that all algorithms are estimating parameters. So it doesn't mean that they try to do their best, but it doesn't mean that they will succeed. So polishing is a kind of poor man's solution. If you could have perfect data from the very beginning, that you would be in a much better situation. Then also, I always thought that we should avoid eyes in our micrographs. So if you have eyes, the more eyes you have, the more difficult it will be to align your particles. Actually, if you have very thick eyes, the particle alignment is really, really tough. This is not too thick eyes. You can see it here also in the power spectra. So most power spectra, they have a ring around 3 angstroms. That means that there is a layer of eyes there. And if you are very strict about having no eyes at all, then in this particular data set, you would have almost no micrographs. And then before I was really really a critic with these having eyes, but now with this data set I have changed my mind a bit. So if the eyes is not that thick that it prevents the particle alignment, then it is not that bad to have eyes, because otherwise you would be throwing many particles. So if your eyes is such that you still can align your particles, that's fine, you can have them. And here you have an example of the peaking. This is done with XMIP, and it depends on the quality of the peaking. Really depends on the initial particles. So as you know, for instance, in XMIP, we learn from the user the kind of particles he's picking. So if in the training set you are not very careful, you can have very bad pickings, and I would say this is a relatively bad picking. You can repeat the same picking with better training particles, and instead of having 1.2 millions, you would have around 700,000. So yeah, but let's say that this is our picking. So and it is good to illustrate the tools that you can have in Scipion to get rid of a bad picking. And also here, this was one of the few data sets where I have seen this ringing here. So this ringing here, we think it is coming from the aperture of the microscope. So for some reason, you are seeing there the oscillations coming from the aperture. And so we thought, okay, so you can only get the particles from the central region where you don't see these oscillations of the aperture, because otherwise these oscillations will drive the alignment and you will get a crap 3D reconstruction. But actually that was not the case. And I was also very surprised with that. And I think it goes again with this idea of the eyes. So if your perturbations eyes or aperture are not that strong that they prevent the particle alignment, they don't matter. So here is another picking with 700,000. This one was done with Crayola, and let's see how these two are done in the project. So, and this is an interesting idea. You don't need, for instance, let's say that you have an acquisition slot in the micrograph of 1 day. So when you have the first micrographs, and here we waited for 700 micrographs, but actually we peaked only on the first 10 or 15. So you peak your your particles in the first 10, 15, and then you can go to automatic picking, and this automatic picking is taking the model from the manual picking. So this manual picking is fixed. So you have picked the first 15 until you are happy with the picking. And then this second picking is taking the micrographs that are coming from the motion correction. So that means that as new micrographs appear in the motion correction, the auto picking will also pick particles in those new micrographs. And the same with Criollo. Criollo, I think it is also in streaming. So you can do both pickings at the same time. And here, let's see the parameters of Criollo. I hope I have the plugin. Yeah. So yeah, this is coming. So you can have different training. So you can either take a generally trained picking for cryo-EM, or you can actually train your model. So when you go to the plugin of Crayola, there is a training protocol, or you can have a general picking model for negative staining, and so you don't have to train. And there are advantages. Normally, I haven't seen a project where you really need to train. And normally the general models, they work correctly. The rest of parameters, they work also correctly. The one that is very important is the box size. And for the box size, let's see this. Let's take this one. That probably will be faster. So you can follow different strategies to do the picking. So I'll show you the one I like. So we used here, wasn't me, it was somebody else, but we used here 4 micrographs for picking. And you see that even in the first one, there were a lot of particles away that he didn't correct. That is why we got 1 million particles. So the training area was this one. And after the training area, it is very good that you correct for the mistakes of the picking algorithm. So the thing is that you can, I like to do like this. I don't mean this is the only way. So when picking, I would say a box that is relatively tight to the particle is good, because that will allow you to pick 2 particles that are relatively close to each other. And then later, you can decide whether to reject those or whether to keep them, depending on how many particles you have that are relatively isolated with respect to particles that have nearby particles. And so it gives you more flexibility. And if you take a very big box size, so the algorithm is learning what you are picking. So if you pick very isolated particles with a large box size around, it will look for isolated particles with a large empty area around, and then you may lose many of your particles. Okay, so then Our traditional consensus was this one. You know that in Scipion, if you do Control F, you can find your protocols. So whenever this is coming, consensus. So we had the peak consensus, and the peaking consensus was relatively naive. So all it was checking was that the coordinates were closer than some threshold. So you could take a few picking results, and then all those pickings that were closer, all those coordinates that were closer than 10 pixels, they were considered to be pointing to the same particle, or to the same location at least. And this consensus number gave you a little bit of flexibility of how, what coordinates to keep. So let's say that you had two pickings like these ones. So this -1 was equivalent to 2. So -1 was the maximum. And it meant that you believed that something was a true coordinate if it was found by the two pickings. And then you could relax it and say, no, just by one. If you have 3 pickings, 4 pickings, you could be relatively creative there and say, I believe something is a coordinate if it has been found by at least 2 of them or by any one of them. So it was very flexible, but very naive. So it was just checking coordinates. But now we recently published a paper in which we take the 2 sets of coordinates and we use them to train a neural network. And this neural network will assume that a coordinate that has been found by the 2 algorithms is more likely to be a particle, and a coordinate that is found by only one of those pickings, it is probably a mistake. And so it looks more or less like the one that we had before, but now it has much more capabilities. So as all neural networks, you can start from a pre-trained network that anyway we train, or you can start from scratch, completely scratch. So the network is initialized with random weights, and it doesn't consider any previous knowledge of how a particle looks like typically in a micrograph. Or you may do a deep consensus. It will generate this deep learning model, and then you can use another deep consensus using the model from the previous run. So normally the most typical example is this one with pre-trained, and then you can use some pre-processing steps, whether to ignore the CTF or not, whether to invert the micrograph, and some parameters for the learning, and this is very interesting. So we have pre-compiled a set of negative examples. So we have gone over a number of data sets, and we have found contaminations, carbon etches, and aggregations of particles, and we have selected like a set of 5,000, 10,000 of these particles, and the neural network is also learning to discriminate between these very bad things from the particles that have been selected by the 2 algorithms here. So the output of this algorithm is a set of coordinates, and then all the input particles, they are assigned a score between 0 and 1, meaning 0 that the algorithm believes that is not a particle, and 1 that it believes that it's a true particle. And then you choose your coordinates that you want. So for instance, here you see we entered with 1.2 millions, 0.7 millions. There were 1.3 millions that were different, that they had different coordinates. So this 0.7 was a subset of the other one. And then you see that the ones with 0 are completely crap things. And then if you go to the other end, it believes that there is a particle. Doesn't mean that it is your particle. So, but there is certainly something there. And then if these are contaminations or things that you don't want to keep, you would have to clean it later. And what we have found useful to choose this threshold is the following. So you choose the scoring assigned by deep learning. And this takes some time because it is a plot with 1.3 million values. You're pretty quiet. I don't know if it is because no, you can talk. But it will be coming. Okay, so then I chose a threshold of 0.99, and you will see now in the plot why. And while this is coming, you can continue a bit. So here you have the result of the deep consensus. So you can see that this is the same micrograph in one of the pickings, in the other picking, and the one that deep consensus has selected. And it is not perfect, but it is much better than any of the other two. And then we also have another, here is the plot. And here you see how to choose the threshold. So normally it is somewhere where there is a change of regime. So it would be somewhere around here. So this is 0.94, 95. I chose 0.99. So I chose something like this. So just the flat part of all the coordinates. And the way to choose those particles is the traditional way in Cyprian. So you go to the point where you see your threshold, then you right-click, select from here, and then you can create your new set. Or an alternative way is select to here, then disable, and then you create your set of coordinates. And you know that sometimes it is very difficult to move with the mouse, so you can use this field there to go to a specific row that you want. So let's say that you want to go to the row 1 million, then you write 1 million up there, and then you are in that row. Okay, so this micrograph cleaner is an algorithm also based on deep learning that tries to identify carbon edges, aggregations, contaminations, and so on. So it removes the coordinates that are coming from those areas, and it went just like 5% down. So it removed 5% of the data. And let's see that protocol here. So this is the micrograph cleaner. And the analyzed results is this is because of this connection. So you can see a histogram of the scores that this micrograph cleaner has assigned to each one of the coordinates. So if the score is high, that means that is a good particle. If the score is low, it is a bad particle. So you see that most of the particles or coordinates have a score above 0.9. We have been rather conservative not to remove many particles, and by default we suggest 0.8, but I use 0.9 looking at the histogram. And when you click on the eye, a new set of coordinates will be generated. So when you run the protocol, it generates this set of coordinates where you have all the coordinates from the input, but now with this score. And when you press on the eye, after choosing your threshold, you have your new set of coordinates with only those with a score better than that. By the way, you know that you can color your boxes using the labels in Scipion. So you can create new labels here. So you create the labels that you like, and then you can choose any one of those labels and assign it to the box that you have selected. And to see the colors of the labels, you can go to here, toggle color mode, and then there are different color modes. This is the default one that tells you whether the protocol has finished or not. And this one is with your labels. Okay, so now we have coordinates. Let's go for particles. And for particles, and again, there is not a unique way to do this. This is the way I did. I find it useful, but doesn't mean that you have to do it like that. So I normally extract the particles at a small size, and with this relatively tight box. So you see that 280 was the tight box size that we chose when picking the particles, and then I did a downsampling by a factor 2, and the reason is that for doing the 2D cleaning, you don't need to be really precise in going to very high resolution. So making particles smaller makes a safer space, makes all algorithms faster, and there is an even more fundamental reason, that is you are removing noise. So when we look at the power spectra, the high frequencies were mostly dominated by noise. There was almost no signal. So if you remove the high frequencies, you are removing noise so that algorithms have a better time trying to align particles and to decide what is seen there. And depending on which algorithm you want to use, when you extract, you may need to phase flip or not. We think that phase flipping, or at least me, I think that phase flipping is better performed at the level of micrograph, because there phase flipping involves some kind of convolution. And convolution means that if you want to deconvolve, you need to know how the surrounding of a particle is, so that you can incorporate that information to perform a proper deconvolution. If you have very tight particles, very tight boxes, then you are missing that information. But it is not a total catastrophe. But I prefer having doing the convolution at the level of micrographs, and this is chosen here. Phase flipping, yes or no. But then it depends on which program you want to use later. Because if you want to use, for instance, CryoSpark, CryoSpark assumes that particles don't have a phase flipping. Reliant doesn't care. XMIP depends for what cares or not. So for the 3D reconstruction, in the released version it cares, in the development version it doesn't. And so I wanted to use CryoSpark for the 2D classification, so I didn't do any phase flipping here. And then you do a classification with CryoSpark. CryoSpark is really, really fast. So you see 400,000 particles were classified in just half an hour. And so it is very fast. Doesn't mean that it produces the best results ever. Actually, no program does. And but the results are pretty understandable. And there are a few things I would like to highlight here. So these are the particles that were coming from the aperture region. These are particles that 14,000 particles that average to this class, and then you see the same for some of them. They look like really the particle you are analyzing. Some of them they look like contaminations, spots, or black dots in the images like this one, and then you choose the classes that you like. So you choose the ones you like and create a new set of particles. And one of the things I would like to say here is that if you don't see high resolution in your 2D classes, it is very, very rare that you will go to high resolution in the 3D reconstruction. So just the first quality filter of your data set would be, I can see small details in my 2D classes. And typically I chose the selected particles, and I wanted to do some other analysis that I'll tell you in a moment. Then I did a second 2D classification, and this time we were discarding many less particles. So most of the classes here, these were the good classes. So the good classes from the first round are now classified. And now you see things that they don't really look like good particles. This ones, but they were in good classes in the previous round. So that is a problem that is known as the attraction problem. So the attraction problem is once a class starts to get a high signal to noise ratio, it attracts many different images to it, even if those images, the signal of those images, doesn't correspond to the signal in the class. And the reason is that since it has so little noise around, this little noise contributes with a small value to the correlation, and then the correlation is higher. So this attraction is really a problem, and you have to be aware of it. Okay, so then with all the discarded classes, images, I joined them, and you see that they are not few. They are just 100,000 particles. So we started with 400. So it is 25% of the data was discarded by this 2D classification. And I wanted to see if I could recover a few of them for the processing data set, but I couldn't. So we can look at the classes. And most of the classes, they look very badly. This may take a while. In the meantime, let me show you some other slides. So here is another interesting idea. So I'll go to, actually, this was going too fast. Yeah, this is what I wanted. So this is the results from the 2D analysis round 1 to the analysis round 2. And this was a CryoSpark. But if you take the same particles classified by CryoSpark and classify with SIL2D, now what you see is that there are many more that have this aperture pattern on top. Actually, when you look at this is the classification. Sorry, this is the classification with the discarded particles. So you see, you don't see any, this few there, but just for, this is just 1% of the input data set. Okay, so if you take the particles coming from cryospark and align them with CL2D, then you see that many more classes have this pattern. So somehow the objective function of CL2D is more sensitive to this pattern, which is there. And actually, there is no, in principle, no a priori knowledge that it has to find a particle that is round in the middle. So it finds images with similar patterns. And this pattern of the aperture was there. And it was in actually 7/8 of the data set. So only 1/8 of the data set didn't have this aperture on top. And again, this was a change of mind for me, because normally I was very strict in the 2D classification. If there is a problem in the 2D classification, I was thinking that will drive the 3D alignment, and then I cannot use those particles for 3D reconstruction. But actually you can. If the pattern is not strong enough to drive the 3D alignment, then these particles can be used. Then this is another idea about whether we should use particles that are completely isolated or particles that have other particles around. And this, for instance, here, this is another data set, not this one. This is a proteasome in which there were many particles close by, and I used particles that were isolated, and this is the 3D reconstruction. This is a slice of it. And on purpose, I chose all those particles, only those particles that have something nearby. And when you do 3D reconstruction, you still get your proteasome, but it's very much corrupted by the information around. So the 3D reconstruction is trying to satisfy all the projections and the full projection, not only the central part where your particle is. It is trying to find a volume that satisfies the best it can all the information present in the image. So this was an extreme case because I only chose particles with nearby things. But in reality, you have a mixture between these two extremes. So depends on what is your proportion of isolated particles. Let's say that your proportion is 90%. So that means that you have a 90% times the correct volume plus 10% a volume that looks really like this. And you are adding both in your final reconstruction. And so this is really something to be aware of. And the same happens with particles that are contaminations, particles that are in the middle of the eyes, or particles that are misaligned. If you are misaligning 10% of your particles, this 10% of your particles reconstruct something that is really, really weird. And the final reconstruction is not very much affected if 90% of the particles are correctly assigned. But if they are, if this percentage is much higher, like 30%, 40%, and these can be really the numbers. We will see it in the next seminar, that the number of particles that agree in the angular assignment can be as low as 50% or 40% only. Then you are having this effect, and here you have the famous HIV trimer reconstruction, and one of the problems here was using incorrect particles. So using incorrect particles for your 3D reconstruction is also very, very dangerous. Then I went to 3D reconstruction. So we used for that, again, the first step, cryospark is so fast that it is worth it to, while you have many, many particles, it is worth it to use cryospark. And later, you may decide what to use less, what to use later, as you have a better idea of how your particle looks like. But for the first steps, CryoSpark is really, really fast. So I constructed a 3D initial volume, actually not one, but two. And then I got 220,000 going to one structure and 58 going to the other. So this is more or less like 20% of the particles that had survived all these deep learning screening, picking with Criollo, so very sophisticated stuff. And still, either they do not correspond to particles or they cannot be well aligned. So they sum up into a 3D structure that is not so good. And this is an interesting thing. So you get 220 particles going to one class. How do you know these particles are really belonging to this class? Because you know of these, all classifiers have false positives, false negatives. So there are classification mistakes. How do you know that these ones really go to this class? And the only way to know, and there is no guarantee, but if you repeat the process and all particles get the same label, you don't know if that is the true label, but there is, with the tools you have, that is that classifier, you cannot say that they can have different label. And actually, if you repeat the same process twice, you get the same amount. But interestingly, and this you can do with the 3D consensus in Scipion, not the 220,000 particles that go to one class are not the same 220,000 particles that go in the second run. So the ones that go together, there are only 90% of them. The other 10%, they are jumping between one class or the other. And this is consistent with the concept of having classification errors. And you may do this only twice, as I did. You may do it 3 times, 4 times, and then only take the intersections of those. And this is another, let me show it again. This is another example with a different protein. This is a ribosome, and the head of this ribosome is moving. And when you do a 3D classification, you run it once, and this, I don't remember if it is CryoSpark or Reliant, but any one of the two, it doesn't matter. So you run it once, and you get this distribution of particles. So almost half of them go into one class, the other half goes to the other class, and a few of them go to a crab class. If you don't repeat this process, you would be perfectly happy with this result, and you might construct your biological history or your biological story about what is the meaning of these two classes and so on. But then you repeat the process a second time, and now you get a totally different classification. It is almost 1/3, 1/3, 1/3. Now you are suspicious about this classification. You repeat it once again. Now you get 1/3, 1/3, 1/3. But now that you know that even if the number of particles looks more or less the same between classification 2 and classification 3, the particles themselves may not be the same. And actually, that is the case. When you compute the 3D consensus is dividing the original data set into subsets that they always get the same label. So now this is what you see. There is a whole, almost continuous classification. So, and this is consistent with this continuous angular assignment. So the angular, the discrete classifications that you get are rather unstable. And this may be the case for some particular data sets. For some others, they might be very stable. But what you have is this effect of, if I put in a class particles that do not belong to the class, then I have this effect of a proportion of the particles are correctly assigned, and then another proportion are incorrectly assigned. And what I'm seeing is the mixture of the two. So let's see how this is run in Scipion. So yeah, now I extracted here there are a couple of steps that are kind of administrative steps, but I find them very useful. So some of the coordinates, they have been found twice on the same particle, but because they are farther apart at your threshold, you cannot distinguish them. But when you have performed the 2D class alignment, you align your particles to the class those classes are normally centered. So now you can better realize whether your particles are really the same or not. So first you center your particles, and for that you need an input that is a set of classes, and it produces the same set of classes, but now with the center particles, the set of particles now with that have been interpolated to the center, and it produces a set of coordinates that are corrected and now pointing better to the center of the particle. And now you can have this other protocol that is remove duplicates, that removes in this case like 3% of the particles that were repeated. They were really pointing to the same particle. Okay, so now you extract your particles, and now it is where you put a bigger box, because these will be the particles that you will use for the 3D reconstruction, for the serious 3D reconstruction. And there, as we know that we have to correct for the CTF, and then that needs a deconvolution, and you need the information around. Now the box is is bigger than what you use at the beginning. At the beginning, I was using 280, and now I'm using 400. The CTF more or less is of a size that the radius of the pixel size of the PSF is around 30-40 angstroms. So you need at least this extra space to be able to deconvolve it. And you hope that this extra information around doesn't drive the angular assignment. And for that, you can use masks during the 3D reconstruction. So here you have these protocols that I told you. So you construct two initial models with dividing them into two 3D classes. Let's edit the protocol to see if there are some special parameters. But normally, I never touch the default parameters. Basically, because I don't have so much experience with these algorithms that are not so XMIP based. But yeah, some other people might have better criteria to choose these parameters. But normally the default ones, they work pretty well. So the main one is this one. What is the number of classes that you want to have at the end? And this is a range of resolution. So your first reconstruction will be at 35 angstroms, and then at maximum you want the algorithm to go up to 12, because we are just trying to construct initial volumes. And the rest, I assume that they are normally fine. If the particles are symmetric, sometimes if you use a C1 reconstruction, they have a hard time. And with symmetries, I have had a few failures of cryospark, particularly in some data sets, but it doesn't mean that it always fails. So you do that process once, you do the process again, and then you can choose the ones that are common between these two. And you see that the input to these consensus classes is pretty simple. So it is just the set of classes 3D that you have constructed so far. And then the output is a small subset that they always got the same label. So these two have these 200,000 particles, they always go to the good structure. Doesn't mean that they really belong to that good structure, because you know of this attraction problem that in the next seminar we will see how to try to identify it. And then the remaining particles, they were going to these bad classes. So now you take the 200,000 that you trust, and you would go to 3D reconstruction. So this was the end of the workflow that I wanted to show you today. And here is a very interesting thing. All those 200,000 particles, they are giving very good, or not very good, but a decent 3D reconstruction. But now, if you take those particles and do 2D classification again, this is what you get. Most of the particles have either a pattern or a gradient or a nearby particle, or so there are many mistakes in these particles, and still they produce a good volume. And again, this is this idea that has appeared a few times. If these patterns do not disturb the 3D angular alignment, then, for instance, all these particles, they have this pattern of the aperture. But if the particles are randomly oriented, the pattern of the aperture will cancel, because it is oscillating, and then on average it will give a zero mean. So in 2D that is different, because in 2D we are trying to align the information that we have there, and the pattern is a very strong 2D information. But if this 2D information doesn't prevent the 3D alignment, removing those particles from the very beginning might be removing particles too soon. So I don't mean that any artifact is fine in the 3D reconstruction, but taking the decision too soon, you may be rejecting many particles that could be useful. And so, as conclusions, 2D cleaning is not essential in this sense, that there might be 2D patterns that are bad, but still they don't prevent the 3D reconstruction from being good. And the defocus has to be really good, and probably the same happens with the trajectories, but as we don't have so far a way to compare trajectories, I couldn't do this comparison. And this thing that 2D cleaning is not essential doesn't mean that you can put everything into the algorithm, in the 3D reconstruction algorithm, and it will manage to produce the best resolution. You will always have this error, this kind of problem. 90% of the data is good, 10% is bad. What you have is a mixture in your 3D structure. How important is that mixture? Depends on what is your percentage. But if you want to go to really high resolution, you need to do everything perfect from the beginning to the end. This is not only my work. This is the work of a lot of people in the lab. This is how the lab used to look like. Now it looks more like this. And I'm open for questions. I was open for questions all the time, but you didn't do. Any comment on this? Just unmute yourself. And yeah, the idea of these seminars is that there is a fluid two-way communication. Otherwise, if I'm speaking alone, they're less interesting.
Carlos.
Yeah.
Maybe I can ask. I just probably maybe didn't get it well. What was the public aim of this? Because it seemed to be that you went a bit more detailed than I expected. But therefore, I would like to ask you if it's possible that you with this example of workflow to share with us somehow that we could see more or less the whole workflow, because I couldn't really make sense of everything at the pace that you were talking. So if you could just like somehow share the tree, this example of a tree, that would be great.
Yeah, I will. You know, there is a repository of workflows. It is here, Scipion ecosystem, workflow repository. And mine is not there, but I will upload it.
Okay. Yeah, perfect then. Yes. Okay, I didn't know about this section. Thank you.
There is a comment by Grigory that the GCTF and CTF find they have completely different criteria for this maximum resolution. So he may want to comment on those, because actually I don't know the very little details of the implementation of those two. I don't know exactly what they mean by maximum resolution. I know what we mean. We mean energy. So, but I don't know exactly GCTF and CTF find what they mean. So maybe if Grigory is still around, he may want to comment. So Grigory seems to have left. What else?
Hello, this is Adriana Miele. I have a question on the box size, but maybe I got it wrong. So you said that it's better to have a tight box size for the picking, but then when are you going to enlarge it? Only at the 3D or also in the 2D analysis?
It's up to you. I prefer doing the 2D analysis on tight boxes, so I concentrate on what is seen around just around the particle and just a bit around it. And then for the 3D analysis, when you have to deconvolve for the PSF, you need the information around. So definitely there you need the space, the extra space.
But you want to take off those particles which are too close together, which have something too close together.
Yeah, you know, you have seen this extreme case where I only use these particles, and they drive the alignment, and the 3D reconstruction tries to satisfy those nearby particles too. So, yeah, ideally, you know, single particle analysis. Single means isolated. So the ideal thing and the theory goes for isolated particles, but sometimes you don't have them. But then at least you have to be aware that you have a mixture in your 3D reconstruction.
Thank you.
What else? Is there anything that you miss for this part of the workflow that you normally like to do with your particles, and then you cannot find it in Scipion? Or any complaint that you have about Scipion? Anything that you would like to improve?
Maybe I can just make a question. It's a bit out of the topic, I think.
Sure.
But I run a 3D classification job on Scipion, but with Relion. And it's interesting that in the log file I get an error which says XMIP error. What does that mean then?
And it is using Relion.
Yeah.
Very likely it is.
I got confused. I don't even have XMIP in the workflow.
Yeah, very likely it is that Scipion relies on XMIP for reading images, reading metadata, and so on. And maybe if the metadata has a problem or the image or whatever, for some internal operations of Cypion, it is using XMIP. So even if it is you're using a plugin of Relion, at some intermediate steps, it might be using XMIP for some small operation.
Interesting. I didn't know. Yes, it complained about a matrix 4x4, which is not invertible. So yes, that must be something in the metadata. And this was data that initially was imported from CryoSpark. Exported from CryoSpark and imported in.
If you have an error that is reproducible, that is very good, because we can analyze that particular error, why you're getting it.
Okay, then I can get in contact with you.
You know this address, Cypion at I2PC .es?
Yeah.
No, Cypion at cmb.csic.es.
I guess this one I can find it on the website.
Yeah, I can find it here. Cypion at cmb CPS. That's it. So if you send us reproducible errors, we can fix them. If the error is random, they are much more difficult to catch.
Yes. No, but this has been already, I mean, I cannot get unstuck of this, but probably something in the metadata, and I don't have this knowledge to clean it there.
Yeah.
And I will get in touch with you via this.
But for instance, sometimes, and it happens in those places where we identify, we try to fix it, but there are places that escape. That is, for instance, let's say that you have a metadata with 500,000 particles, and when you are importing them, there is a problem in just one line, so that line is clearly incorrect. But that doesn't mean that the protocol should fail. So just skip that line. So depending on what is the error, we can try to ignore it or not, or try to fix it.
Yeah.
It is we make some assumption that is not fulfilled by the import, or
Okay, yeah. In this case, the protocol failed, so I couldn't go further.
Yeah.
Okay, thank you.
No problem. Anything else? No? If not, let me thank you again. And in a couple of weeks, we will have another seminar. And this time, normally we would like to interleave these more technical based on Cypion and those more based on workflows and image processing. But the next seminar is the second part of this one, so it will be also on image processing. And you have the full list of seminars in the I2PC I2PC.es webpage. And yes, so see you next time. And thanks a lot.
Thank you, Carlos. See you.
Bye.
Hello.